We're now going to take a look at one application of derivatives, and that is related rates. So imagine you have a camera pointing at a performer on a stage. As that performer moves, the camera is going to need to rotate. If we know how fast the person is walking, can we figure out how fast the camera needs to rotate? This is an example of a related rates problem. We know the rate of change of something, in this case, how the person is moving, and we want to find the rate of change of something else, of the camera. Both of these rates of change are derivatives, and they are related. In this case, they're related through the geometry shown in this picture. It turns out we can use the relationship between our derivatives to see how one rate of change is related to another. So we're going to come back to this specific problem, but I want to start by looking at a problem that is a little bit more general, just to show you the mathematics, the approach that we're going to take, and then we'll come back to that application. So the example I want to do says, find dx dt when x equals -1 and y equals 10, if dy dt equals -3 and x squared y equals 10. So we are given one rate of change, one derivative. We're told that dy dt is -3, and we're asked to find another derivative, another rate of change, dx dt. So x and y are both functions of t. They both depend on t. And we are given a relationship between x and y through the equation x squared times y equals 10. So what we're going to do to solve this problem is we are going to take the derivative of that equation with respect to t. And so we are going to have to use our chain rule, kind of like our implicit differentiation as well, because x and y are actually functions of t. So if I take the derivative of x squared times y, well, that's a product, so I'm going to have to use my product rule. F is x squared, g is y. So f prime would be 2x. But now that x is actually a function of t, and we're really taking the derivative with respect to t, I'm going to have to multiply by dx dt. And then I do something similar to find g prime. The derivative of y should just be 1 times dy dt. Plugging this into my product rule, I get f prime times g, so 2x dx dt times y plus g prime times f, which is dy dt times x squared. Then if I take the derivative of the right-hand side of this equation is just a constant 10, and I'm going to get 0. So now that I've taken the derivative, I actually have a relationship between my derivatives. So to finish this problem, I can just plug in the values given and solve for the unknown. So we're told that x is -1. So everywhere I see an x, I'm going to put in a -1. And we're told that y is 10, so 10 goes in for y, and dy dt is -3. I don't know what dx dt is, and that's what we're solving for. So this is now something we can solve for dx dt. I've got 2 times -1 times 10, that's -20 dx dt, and then plus -3 times -1 squared is -3, and that equals 0. So add 3 to both sides, divide by -20, and my final answer is dx dt equals -3 divided by 20. So the first example I want to do says a plane is flying horizontally at a height of 1 mile and a speed of 500 miles per hour. It passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles from the station. So I'm going to start by trying to draw a picture. So we have our plane flying horizontally. It's 1 mile above a station. And so the plane is actually moving. It's flying at a speed or a rate of 500 miles per hour. All right, so the rate that I'm given is this 500 miles per hour. I know that this is a rate for two reasons. One, it says it's a speed, so that's a rate of change or a derivative. But also the units, it has a compound unit of miles per hour. So it's describing how the position of the airplane is changing with respect to time. And so if I want to say that the distance the airplane has traveled is x, then this 500 miles per hour tells me how x is changing. That should be my dx dt. So the derivative that was given to me in this problem, the thing that I know, is the distance the plane has traveled, dx dt, is increasing at a rate of 500 miles per hour. So that's the derivative I know. Now there should be a derivative that I'm trying to find. And let's see right here, this word rate is a clue. Find the rate at which the distance from the plane to the station is increasing. So when the airplane is directly overhead of the station, that distance is 1 mile. But as that airplane travels to the right, that distance from the station is going to increase. And so I'm going to go ahead and call that distance d. And so I want to know, how is that distance changing? In other words, I am trying to find dd dt. How is that distance changing with respect to time? And I care about that rate of change at the instant in time that the airplane is 2 miles from the station. So I care about that when d equals 2. So the first step in all of these problems is to draw a picture and try to identify, there should be a derivative that you are given, a rate of change that you're given, and then there should be a derivative that you're trying to find. Once you have those two things written down, what you know and what you want to find, the next step is to try to write a relationship between the variables. So the variable in my derivative that I know is x, and the variable in the derivative that I want to find is d. So I need to write an equation that relates x to d. And this is where I'm going to look at my picture. So I do want to point out that x and d are both variables. As the airplane is moving, those are things that are changing. That's why I'm using letters to represent those distances. Whereas this, I guess it's my straight vertical distance from the station to the plane, that's always 1 mile. That altitude of the airplane is constant. So that's why I'm not using a variable for this distance I have labeled as 1 mile. Now when I look at this picture, I see a right triangle, and so I can get my equation using my Pythagorean theorem. I know that a squared plus b squared is c squared. Or in this case, 1 squared plus x squared is d squared. So now I have my relationship between my variables. The next step is to take the derivative of that relationship. So the 1 squared is just a constant. That has a derivative of 0. X squared. X is actually a function of time. So when I take my derivative, I'm going to get 2x and then times dx dt equals, and then the derivative of d squared, d is also a function of time, so that's going to become 2d times dd dt. Okay, so just to recap what we've done, we identified the derivative we know and the derivative we want to find. We came up with a relationship between those variables. Then we took the derivative of that relationship with respect to t. Finally, we're going to try to plug things in so we can solve for the derivative that we want to find. In this case, we want to find dd dt. So I am given dx dt, that was 500, so I'll be able to plug that in. I was given d is 2 at the instant in time I care about. But I actually don't know what I'm going to plug in for x. So again, we're trying to find this dt. That's what I want to solve for. So I need to plug in numbers for all of the other variables listed. And I know 2 out of 3 of them. I know d is 2, dx dt is 500. I don't know x. But it turns out we can actually solve for x, because when d is 2, I can use this right triangle to figure out what x is. Again, using that Pythagorean formula. I even have my equation written down right here in the middle of the screen. So 1 squared plus x squared has to equal 2 squared at the instant I care about. Or 1 plus x squared is 4, x squared is 3, x is root 3. And so now that I know what x is at that instant in time we care about, I can plug all my numbers in. So I've got 2 root 3 times 500 has to equal 2 times 2 times dd dt. And we can solve for dd dt now. We've got, let's see, 1,000 root 3 equals 4 dd dt. Divide both sides by 4. So that distance is changing at a rate of 250 root 3 miles per hour. All right, I'd like to come back to that problem that we started the video with. So we've got our camera pointed at a stage. Just to put some numbers into this problem, let's say that our camera is sitting here at the origin, just like I have in my picture. And it's filming this person that's on the stage. And the stage is exactly 4 meters away from the camera. So we're on that line y equals 4. That performer is starting right here at the point 1, 4. And they're walking to the right. So this distance, which I'm calling x, as that performer moves, is going to be increasing. I am told that the performer is walking at a speed of 2 meters per second. That's a rate of change. The word speed and the units, meters per second, are telling me that that is a rate of change or a derivative. Okay, we're told that theta is the angle. Right here on my picture, it's the angle between the cameras, kind of, I guess we could call that what, central viewing line, like straight at the stage, and then to where it has to point basically to see that performer. And the question is, how fast must this camera rotate in radians per second at the instant in time when the performer is at the point 64? Okay, so there are a lot of words on the screen, so let's try to simplify this into something that we can solve. So in this problem, there should be a rate that we are given, and that rate is the speed the person is walking. So if we say that this distance I have labeled in my picture is x, if this person is walking to the right, x is getting bigger at a rate of 2 meters per second. So we know dx dt, so x is changing with respect to time at a rate of 2 meters per second. There should also be a derivative we're trying to find, and that is how fast must the camera rotate? I'm trying to find d theta dt. So I know dx dt, I want to find d theta dt, and I want to find d theta dt when that person is at the point 64. So when x is 6. So when they're all the way over here, I guess right there at the edge, x equals 6. Okay, so again, we want to know what is d theta dt when x is 6, and we're told dx dt is 2. All right, so that is the problem we're trying to solve. And so now we're ready to go through our process. The derivative we know involves x. The derivative we want to find has a theta. So I have to write an equation that relates theta to x. So looking at my picture here, if x is this horizontal distance that the performer has traveled. Theta is my angle. And if that stage is up here at y = 4, then this, I guess, vertical distance in my picture, or distance, straight line distance from the camera to the stage, has to be 4 meters. And so once again, I see a right triangle. And if I want to relate theta to x, I can use the tangent function. I know tangent is opposite over adjacent. So in this case, tangent of theta has to equal x divided by 4. And there's my equation that relates x and theta. Now I'm going to take the derivative of that equation. The derivative of tangent theta is secant squared theta, but theta is a function of time, so I have to multiply by d theta dt. The derivative of x over 4, or 1/4 x, is 1/4, and then times dx dt. All right, once again, now that I have my derivative, I'm going to try to plug things in. And so we want to solve for d theta dt. We know dx dt is 2. The other variable in this equation is theta. I'm going to have to plug something in for theta. So just like in the last example, I'm going to have to do a little bit more work to try to figure out what is theta at the time I care about, when x is 6. So when x is 6, I can actually figure out what theta is using that same tangent relationship. Tangent theta is opposite over adjacent. So when x is 6, tan theta will equal 6 divided by 4, which is the same as 3 over 2. I can solve this for theta by taking the inverse tangent. So theta has to equal inverse tangent of 3 over 2. If you want to put that into your calculator, you can, or you can wait and do the calculator work all at once at the end. I put it into my calculator and I got approximately 0.9828 radians. So now that I know what theta is, I can plug everything into my equation. I've got secant squared of 0.9828 times d theta dt equals 1/4 times 2. This is something that we can solve for d theta dt. That secant squared theta is the same as 1 over cosine squared theta. So I've got 1 over cosine squared of 0.9828 times d theta dt equals 2 over 4. So if I want to solve for d theta dt, I could just multiply both sides by that cosine squared quantity. And so 2 over 4, or a half, times cosine squared of that angle. I'm going to put that into my calculator, and I got approximately 0.15, and this would be radians per second. And so that is telling me how much that angle needs to increase so that it stays focused on that person that is walking at a rate of 2 meters per second. I've got one more example to show you. A conical tank with a radius of 2 meters and a height of 4 meters. I have that drawn. So we've got a tank that is a cone. The height is 4 meters. And the radius is 2 meters. And we've got water in this tank. Water is leaking out of the tank at a rate of 1.5 cubic meters per minute. Find the rate at which the water level, or the height of the water, is dropping when the water is 2 meters deep. Okay, so the thing that's constant here is the size of this tank. It has a height of 4 meters and a radius of 2 meters. The parts that are changing are the dimensions of the water. The water level is changing. So there's going to be like this little radius, this little height of that water level. That's going to change as the water leaks out of this tank. So just like in the previous problems, I'm going to start by trying to find the derivative that I know. And what is the derivative that I want to find? Well, I am given a rate, so I see the word rate, that's a clue that that is a derivative, 1.5 cubic meters per minute. That's how the amount of water is leaking. This is going to be a volume of water. I know it's volume because of the units. Meters cubed is a volume unit. I also know it's a volume because we have a three-dimensional region of water, and we're describing how that three-dimensional object is changing in size. So that would be a volume. Although for me, the units is really how I determine what that is. So I know that dV dt equals negative 1.5 meters cubed per minute. And I made it negative because if the water is leaking out, then the volume is actually getting smaller. What am I trying to find? I'm trying to find how the water level is changing. The water level would be the height of that water. So I want to find dH dt, and I want to find that when the water level is 2 meters, when h equals 2. So I have identified the derivative I know and the derivative I want to find. I have a v and an h, so I need an equation that relates v and h. And so I just went and looked up how do I find the volume of a cone. It is volume equals 1/3 pi r squared h. So in this equation, I am relating v to h, but I have an extra variable in there, this r, and this represents the radius of that water. And that is a variable. That's actually something that's changing with time. As the water level leaks, that radius is going to get smaller as well. So I really want my equation to only have v's and h's because those are the two derivatives I want to work with here. So I'm going to see if I can get rid of this r. And what I've done is I just kind of took a slice of this picture of this cone, just like a little, I guess it's like a cross section, and zoomed in to try to make a point. So we know that we've got a cone and the height is 4. So distance is 4 to the top and the radius is 2. And so I can draw like a little triangle using that height and that radius, and then there's the side of my cone. And the water sitting in that tank also makes a triangle with a height of h and a radius of r. These two triangles are what we call similar triangles. They have the exact same shape or the exact same angles, but they have different sizes. And the sides of similar triangles are always proportional. So that means 2 is to 4 as r is to h. So I can write a ratio describing the fact that r to h has to equal 2 to 4. And then I can solve this. I could cross multiply. 2 times h has to equal 4 times r. And I can solve for r by dividing both sides by 4. I get r equals 2 over 4 or a half h. So for this little blue triangle, the radius is always going to be half of the height. And so what I'm going to do is go ahead and plug that into my volume equation. I'm going to replace this r with 1/2 h. So now I have my volume is 1/3 pi times 1/2 h squared times h. We can go ahead and simplify that because 1/2 times 1/2 is a 4th, and then we've got an h squared. So this becomes 1/3 pi times a 4th, that's a 12th pi, and then h squared times h is h to the 3rd. So my volume equation becomes pi over 12 times h to the 3rd. So finally, I have an equation that relates v and h. I'm going to go ahead and take the derivative of that equation. The derivative of v would be dv dt, and then I have that pi over 12, that's a constant. For the h to the 3rd, I bring down the 3, so 3h squared, and then times dh dt. Finally, I can start plugging numbers in. I know dv dt is negative 1.5. I know that h is 2. and this is something that we can solve now for dH dt. I did go ahead and cancel a common factor of 3 with the 12, so I simplified that constant to pi over 4. So I've got, let's see, negative 1.5 equals pi over 4 times 2 squared times dH dt, or negative 1.5 equals pi times dH dt. Divide both sides by pi. So dH dt equals approximately negative 0.48 meters per minute. That negative is telling me the height is decreasing, so the level of the water is dropping by a rate that's just under a half a meter per minute. All right, as always, please let me know if you have any questions about this video.